G'day, this is the first video of two which will cover all calculations associated with the electric fields inquiry question. In this video, we're going to be starting to unpack dot points 4.1, 3, and 4, which look at quantitative relationships that exist to describe charges and how they behave in electric fields. In this first video, what we're going to be looking to do first is define a charge, then be able to define electric field quantitatively, and as a result, calculate forces that can be applied as well as resultant accelerations to charges when they're placed in an electric field. Further to that, we're then going to apply these same concepts to Coulomb's law, which quantitatively describes how point charges behave when they're able to interact with another point charge. So first, let's talk about this concept of charge. It is a concept that we've sort of talked around in previous topics, not just in the Year 11 course, but also in Years 7 to 10 in science. It is actually something that is quantifiable and measurable, and we measure charge in coulombs. Generally speaking, we've just boiled down these charges to call them +1 or -1, or multiples, or some sort of whole number charge. We can see here that in our datasheet we have the charge of an electron displayed, QE. Q always stands for charge, E here standing for electrons. And this charge here is -1.602 times 10 to the -19 coulombs. So one electron by itself does not have a significant amount of charge measured in coulombs, but obviously when you combine large numbers of electrons all together, it will result in large charges eventually. It's important to note that protons have equal charge to electrons. The only difference is the magnitude of their charge. Therefore, charge of a proton, QP, would just be 1.602 times 10 to the -19, a positive version of QE. And for atoms, which are charged depending on the relative number of electrons and protons, it's fair to assume that atoms should only have charges which are multiples of QE. So for example, if we have an atom with 2 extra electrons, that means its overall charge is going to be 2 times the charge of a single electron. In the previous video, we began to explore the idea that charged objects generate electric fields. In a more quantitative perspective, we can describe an electric field as the measurement of the force experienced by a particle which is currently present in the electric field per unit charge of the particle. The simplest equation that we have that deals with electric field is the one in the top corner here, which is F is equal to QE. To demonstrate these variables and how they're related, I'm first going to rearrange the equation to make E, the electric field, the subject. In this equation, E stands for the electric field generated by a particle. F stands for the force experienced by a particle in the field. And Q represents the charge of the particle. Now, because force is measured in newtons and charge is measured in coulombs, this means that the units of measurement for an electric field should be newtons per coulomb. Assuming that we know 2 of the variables, we can use this 3-variable equation to calculate for any of the unknowns in given scenarios. One of these scenarios is given in the second dot point. It says an electron is placed in an electric field of 5.4 newtons per coulomb, and that we're to calculate the force applied to the electron and its resulting acceleration. So in this question, I can use F is equal to QE. And before I begin, I'm just going to identify all relevant data to solve the question. So first off, Q in this equation is actually QE, the charge of an electron, which is given in our datasheet and is -1.602 times 10 to the -19 coulombs. The other known value that we have is E, which is the electric field, again describing the force experienced by a particle when it's placed in the field per unit charge. E in this case is 5.4 newtons of force experienced for every coulomb of charge. With this data, I can then substitute and calculate for the force experienced by the electron. And the answer that we get is -8.7 times 10 to the -19 newtons. And the negative here indicates that the direction of the force is going to be opposite in direction to the field. Now, this force may not seem like much. However, we need to consider that we're applying a force on an object which has an extremely small mass. Therefore, in this acceleration part of the calculation, we'll see that this electric field is going to cause ridiculously large motion in the electron. We can calculate this acceleration using the F equals ma formula, Newton's second law. Now, the force was calculated in the previous question, and the mass of the electron is given in our datasheet. From here, I can just substitute. This gives us an acceleration of negative 9.5 times 10 to the 11 meters per second squared. Again, because this acceleration is negative, this indicates that the acceleration is happening in the opposite direction to the field. The other quantitative concept that I want to show you today is quite closely related to our definition of the electric field and forces that are applied to charges in electric fields, and that's Coulomb's law. Specifically, Coulomb's law is able to calculate the forces which are applied on point charges by another point charge which is generating an electric field. This equation is a little bit more involved than the first one and begins to introduce a fair number of other terms that I want to unpack first before we get into a practice question. The equation can be seen here in the datasheet. Notably, new terms include this 4 pi, this epsilon naught symbol, as well as r squared, which we know usually refers to radius. Now, as I unpack this equation and the terms which are present, I'd like you to be imagining a scenario in which we have 2 point charges. In this instance, I'm going to have a positive charge and a negative charge. This one's going to be charge 1. This is going to be charge 2. And when in close proximity to each other, these two charges will generate an electric field, which will look something like this, where our field lines go from positive to negative charge. I'd like to focus on the strength of the electric field for the proton, in other words, charge 1. I'm going to write that as E1. Now we can say that that will be equal to Q1 over 4 pi r squared epsilon naught. Effectively, what we're saying here is that the strength of the electric field depends on a couple of factors. One is how much charge does the proton have? And the other factor is here, how far away are we from that charge? Now, if we were just concerned with the distance away from the charge, we wouldn't need the 4 pi r squared term that we have here. However, this term is reflective of surface area of a sphere, which if we reflect on this diagram here, starts to demonstrate a concept which is quite similar to what we looked at in inverse square law in module 3. Essentially here, electric field strength obeys inverse square law in a very similar way to wave energy. And thus, surface area is a component of this equation which relates the charge of the particle and the distance we are away from that charge to the resulting electric field. So, for example, in this diagram here, we would assume that the electric field at the point R1 is going to be greater than the electric field at the point R2. Effectively, in this scenario, Q, the charge will be the same and constant in both examples. But as we increase the surface area of the sphere, we increase our radius. And that also means that this charge here is going to be spread over a larger area. As a result, as we get further and further away from our point charge, our electric field strength will diminish. And finally, we have epsilon naught here, which is the electric permittivity constant, also known as the permittivity of free space. For the moment, all we need to know about this term is that it is essentially here to make sure that all variables are able to relate to each other and actually work in the equation. It essentially is a constant. Now, this equation here describes the electric field of a point charge depending on how far away we are from it. However, this is not reflective entirely of Coulomb's law, which allows you to, again, calculate the force applied on a point charge by another point charge. Here, what we need to introduce is charge 2, the charge being influenced from the first point charge, as well as the resulting force that it experiences. And we can do that by combining our electric field equation with our first equation that we learned in this video, which is that F is equal to QE. Note here that I have given notation for force, charge, and electric field, which match the charges in the diagram here. Essentially, what we're saying here is the force experienced by charge 2 will be equal to the charge of charge 2 multiplied by the electric field generated by charge 1. And that electric field is again described by Q1, 4 pi r squared, as well as at the permittivity of free space. So effectively here, I will combine those equations and that should give us Coulomb's law. Note that the equation that I've written down here is slightly different from the structure given in the datasheet. I will note the reason that is because in my equation I've just combined all the terms together. However, the equation in the datasheet separates our terms into all of our constant values and all of our variables on the right-hand side. So the last thing for this video is just to quickly show you how we can apply Coulomb's law to a real-life situation. In this question, we're being told that a proton and electron are being placed 6.0 times 10 to the negative 10 meters apart, and we need to calculate the force exerted by the proton on the electron and the electron on the proton. So for this, we'll be using and applying Coulomb's law, and what I'll be doing first is just identifying all of our variables. Note here I've said that Q1 is equal to the charge of the proton and that Q2 is equal to the charge of the electron. Generally speaking, when we use this formula, we mark Q1 as the charge which is generating an electric field and Q2 as the charge which is experiencing a force due to the electric field of Q1. So from here, because we're calculating for force, and force is already the subject of Coulomb's law, as shown in your data sheet, all we need to do is substitute in the appropriate places and calculate. So here, Fp, the force caused by the proton on the electron, is equal to negative 6.4 times 10 to the negative 10 units. And because we have a negative sign, again, similar to the calculation we did previously, this suggests that the force is causing the electron to move towards the proton. This should make sense given in the context of the question, as the proton and electron have opposite charges, and we know that opposite charges attract. Now, to calculate the force exerted by the electron on the proton, here we should appreciate that R should be the same value, that epsilon naught should be the same value, and that while Q1 and Q2 should be flipped and inverted, when substituted into the formula, they don't make any realistic difference to the calculated value at the end, meaning that the force that the electron exerts on the proton, Fe, should also be equal to negative 6.4 times 10 to the negative 10 newtons. Thank you very much. In the next video, we will finish off the electric field calculations that we were not able to complete in this video. But until then, have a good one.